What's going on, everybody? Mr. Diamond, and we are looking at our example problem for Raoults law, dealing with the partial pressure of a gas based on its colligative properties. We have calculate the vapor pressure of a solution made by dissolving 218 grams of glucose, which, in case you forgot, is C6H12O6, in 460 milliliters of water that is at 30 degrees Celsius. Assume the density of water is 1 gram per milliliter. Now, that you should just know that is always the case. You don't need to really assume that. Although I guess it slightly varies based on temperature, but we're kind of not at that point in this class yet. So since we're using Raoults law and we're using water, we need to have this worksheet. You should have gotten it in class. If not, there should be a link to it on Google Classroom. If there is not, please send me an email and yell at me about it. But over here you have temperatures, and then over here you have the pressure of water at that temperature. And you'll notice that as the temperature of the water heats up, we actually expect there to be more evaporation, which will increase the amount of gas above the water, which will then increase the pressure pushing down upon the water. So as you go up, it increases. So for our problem, we're going to be using the pressure of the solution is equal to X of the solvent times the P naught of the solvent, or the original pressure of the solvent. So we know this value because it says it's at 30 degrees Celsius, and so if we come to our paper, at 30 degrees Celsius, we expect water to be 31.82. So this is going to be 31.82 mmHg, millimeters of mercury. Okay, then we need to figure out our mole fraction of our solvent. So let me pull up I think I already had this calculated somewhere. Nope. Okay. Then we'll just go ahead and calculate it. Okay. So mole fraction, not mole solvent. Mole fraction is equal to the moles of the thing that you're caring about divided by the total moles that are found in that whatever the situation is. So in this case, we have 218 grams of glucose, and we have 460 milliliters of water. We actually have to get both of those into our into moles before we can start stepping forward on this problem. So we're going to start with glucose. We have 218 grams of C6H12O6. And then this one, I don't know off the top of my head. I don't really need to Google. I already have those pieces memorized. So we can do 6 times 12.01, that's C. That's 12 times 1.01, that's H. And then plus 6 times 16. And that'll give us 180.18. And I'll put that on bottom because it needs to be grams per 1 mole. And then if we plug that in, 218 divided by our answer from there, we get 1.2099 ... moles of C6H12O6. But then we need to do the same thing with water. This is 460 milliliters. It's a 1-to-1 ratio of milliliters to grams. So we're actually going to have to start with 460 grams of H2O. And then this one, we can do the math in our head, or if not, you can just plug it in. But it's going to be 18.02 grams per 1 mole. That's 2 times 1.01 plus 16. Plug that in. 460 divided by 18.02. We get a whole lot of grams of water. We get 25.2 or 52719 ... And that's moles of water, of H2O. So to find our mole fraction, we're going to take our moles of our thing, which in this case is our 1.2099, divide by our total moles, 1.2099 plus 25.52719. We'll do equals. Remember, this doesn't get multiplied by 100. It's not a percent. So I am going to round because I don't want some of my numbers to be rounded and some of them not to be. So 12.099 divided by 12.099, or 1.20, 0.2, not 12, 0.2099, 1.2099 plus 25 0.52719. And I will get a mole fraction. Oh, sorry. I totally screwed up here. This is actually a mistake that's very common to make, and I didn't make it on purpose, but I definitely made it. We want X of solvent. So even though we normally were working with our solute here, we actually want to put the 25 on top. Definitely didn't do that on purpose. That was definitely just Mr. Diamond making a mistake there. But we want that number on top. It is really hard to get out of the habit, though. I did just recently plow through all of those concentration problems where you care about the solute, so I apologize for that. I felt like that number seemed way too low. Thankfully, we can actually solve for what it is by just doing this. We get 95 or 0.95. Again, not a percentage. So we'll get 0.954748 ... No unit. It's just a mole ratio. So now we can do pressure of our solution is equal to X of the solvent times P naught of the solvent. So our X, 0.954748. I am going to use the full number this time, and then we multiply that by its original, which was 31.82 mmHg. Mole fraction doesn't have a unit, but mmHg does, so our final unit will be in mmHg. 31.82. My point's a little hidden there. We get, didn't even realize I was going off the page. We get, for our final answer, 30.38, blah, 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 or if we check back in our problem, 3 sig figs is what we're looking for, 30.4 mmHg. So it's slightly lower, which makes sense, because if we talked about in the notes, it was vapor pressure lowering, and 30.4 is slightly below what it is at 30, which is 31.82 mmHg. So that is how you do a Raoults law problem. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.